Okay, welcome to the first presentation on the binary number system. And before we talk about the binary number system, let's talk about the decimal numbering system. Now, of course, the word decimal is base 10, deci or 10. So we're talking about a base 10 numbering system. Now, that's what you've been using all your life, and the digits in the decimal numbering system, contrary to what you may believe, are not 1 through 10. The digits are 0 through 9. 0 through 9. 10 is actually a combination of two digits, 1 and 0. So in the decimal numbering system, we start out with the number 0. We don't have anything. The next number is 1. Obviously, should be nothing new to you. And the number after that would be 2, 3, 4, 5, 6, 7, 8, 9. Now in the decimal numbering system, at this point, we are now out of digits. So what are we going to do? Well, what we do is we simply, once we get to 9 and we have to increase, we actually start over with 1, 0. So we start over in what's called the ones position with 0. And in the tens position, we increment one digit. And then we continue to count 1, 1, 1, 2, and so forth until we get to 1, 9. At that point, the ones position is full again. When the ones position is full, we set it back to 0 and increment the tens position 1. Now, this is nothing new. You've been doing this since, of course, elementary school, but you may not think about these things anymore. So we have to think about these things before we get into the binary system. Now let me go ahead and get me a new board here. Now once we start over and we continue counting in decimal, eventually we'll get to 29. What happens at 29? Well, the ones position is full again, right? So we set it back to 0 and increment the tens position. We'll keep doing this, of course, until we get to 99. Once we get to 99, the ones position is full, so it starts back over. Now the tens position is full. It starts back over as well at 0, and we increment the hundreds position. This little pen's hard to write with. The hundreds position. And that's 1, 0, 0 now, 100. And we, of course, continue to count 101, 102, and so forth and so on until we would get to 999. At that point, the ones position, the tens position, and the hundreds position is full. We would now increment the thousands position. Now, of course, the thousands position has been there all along. It's just been 0, right? Just as the hundreds position was available when we were talking about 21. But there's no reason to write a big string of an infinite number of leading zeros before a number. So we only put the digit there when it's necessary. So now we start back over after 999 with 1,000, correct? Now when we write 1,000, what do we really have? What we have is a 0 in the ones position, a 0 in the tens position, a 0 in the hundreds position, and a 1 in the thousands position. Makes sense, right? So if we have 5,343, that means I have 5 thousands, right? 5 thousands. And I have 3 hundreds. And I have 4 tens. And I have 3 ones. Another way of looking at that is anything in this first column here is equal to 10 to the 0 power. Now anything to the 0 power is 1. So this first column is going to be the number times 1. In the second column, it's 10 to the first power. 10 to the first power is equal to 10. So it's going to be the number in the tens column times 10. And that makes sense because in the next column it's 10 squared, right? And 10 squared is equal to 100. So anything in the third column is going to be that number times 100. And in the last column, it's going to be 10 to the third power, which equals 1,000. And that would be the digit times 1,000. So let's look at it this way. It's 5 times 1,000, or 10 to the third power, plus 3 times 10 squared, or 100, plus 4 times 10 to the first power, or 10, plus 1 times 10 to the 0 power, or 1. 1 times 1. And that equals 5,000 plus 300 plus 40 plus, I made a mistake here again, 3. 5,343. Are you going to find something similar when we get to binary? That's why I wanted to show you this. So the number places, which you've been dealing with since kindergarten, is very similar when dealing with binary numbers. Now let's go to binary. In the binary numbering system, we don't have 10 digits. We don't have 0 through 9. All a computer knows is 2 states, on or off. So because of that, we only have 2 digits, and we use the digit 0 and the digit 1. And those are called binary digits. And to shorten it, we use the word bit, which is short for binary digit. 0 and a 1. Now, counting this way is a little odd at first, but just like before, what did we do? When we got from 0 and we got to 9, we were full, so we would put a 0 here and start back over in the next column. The same thing's going to happen in binary. When we start with binary with a 0, the next number is 1. What do? We put a 0 in the ones column, or in the first column, and we increment the second field to a 1. What's the next number? Well, it's 1, 1, not 11. It's 1, 1. And 1, 1 is as big a number as you can represent with 2 columns in binary. So what do? Well, the same thing like when you get to 99. You start back over, right, at 100. You go to 0. You reset both of the first 2 fields, and you increment the third bit. Now, that's not 100. That's 100. That's actually, in decimal, this is what these numbers equal at this time. And I'll show you how I get that in a minute. The next number is 101. Now, why is that the next number? Because there was a 0 in this field, the first bit, so we were able to put a 1 here because we had room. Now, in 101, the first bit position and the last bit position here are full. So we have to reset the first bit position to 0 and increment the second bit position. And that's the next number in sequence, 110, and that's equal to 6. And the next one will be 1, 1, and we have room in the last bit, so that is 1, and that's 7. Now in binary speak, the bit over here on this side is called the LSB, or least significant bit. The bit over here on this side would be called the most significant bit, or the MSB. Now let's clean up the board here, and let me show you what I'm going to this a little bit better. Let me use 4 bits of binary digits. And this time I'll show the leading zeros. In decimal we don't do that very often, but in binary, let's do that. And let me put a line over the top here. And the first position is weighted as 2 to the 0 power. Now why 2? Because we only have 2 digits. In the binary, in decimal, remember the first digit was 10 to the 0 power. So that's worth 2 to the 0 power. This position is worth 2 to the first power. This position is weighted at 2 to the second power. And this position is weighted at 2 to the third. Well, what is that really? Well, 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4. And 2 to the third is 8. So on a 4-bit number, the first 4 bits will be weighted like that in binary. this would be the first binary number, which would be equal to what? Well, it would be 0 times 8 plus 0 times 4 plus 0 times 2 plus 0 times 1. Just like in the decimal number line, we took the digit and multiplied it by the weight to determine what the number was. If you're having trouble with understanding what I'm saying, go back and review the 5,343 number we did. So in this case, 0 plus 0 plus 0 plus 0 is, of course, 0. Let's see if I can clean that one up a little bit. That's a little hard to see. That's equal to 0. Now the next number in sequence is simply 0, 0, 0, 1. Out in the first position, we start with a 1. And that's equal to 0 times 8 plus 0 times 4 plus 0 times 2 plus 1 times 1, which is 1. Now what's the next number? Well, it should be 2, right? Now the end position is full, so we know that's going to be a 0 next time. And we're going to increment this next position by 1 because we can. And these leading guys out here are still 0. Now what is that number value this time? Well, it's 0 times 8 plus 0 times 4 plus 1 times 2 plus 0 times 1. Well, that's 2, right? So you see, we're just simply counting up. 1, 1. Why is that the next number? Because there was the 0 in the last bit meant we could increment the last bit by 1. So we always increment from the farthest to the right we can. And that's going to be 3 because that's 1 times the magic number 2 up here plus 1 times 1. That's 3. What would the next number be? Well, that's going to be a 0 because it's full. The next bit is going to be 0 because it's also full with a binary 1. The 4 position is empty, so we put a 1 in the 4 position, and the leading position, of course, is 8, or 0, because we're not that far along yet. And, of course, 0 times 8 is 0, plus 1 times 4 is 4, plus 0 times 2 is 4, plus 0 times 1, again, is 4. So 4 is the number we're working on now. So let's clean this off again. Alright, so the number line in binary looks like this. Now remember, in decimal it was like 1, 10, 100, 1,000, and so forth. In decimal, or in binary, we only have 2 digits, so they're much smaller initially. So 1, 4, and 8. Let's deal with 4-bit number right now. 0, 0, 0, 0. That's the first number. Remember, that's a binary 0. What would a binary 1 be with 4 bits? Well, the same as it would be with any number of bits, but in this case we would put 3 leading zeros and a 1. The leading zeros are not necessarily required. It just makes it even looking. Try to figure out yourself what's the next number in sequence. We have to put a 0 here and a 1 here because the least significant bit is full at this point. Remember the LSB over here. The least significant bit was full. So we had to put a 0 here and increment the next bit. These would be binary zeros. Now, the least significant bit is no longer full. We can increment that bit for the next count. As we count up 1, we were able to increment the last bit. So we have 0, 0, 1, 1. The next one is 0, 1, 0, 0. The next one is 0, 1, 0, 1. 0, 1, 1, 0, and 0, 1, 1, 1. The first 8. Take a look at the patterns. Notice that the least significant bit alternates every time. 0, 1, 0, 1, 0, 1, 0, 1. Notice the second bit position goes 0, 0, 1, 1, 0, 0, 1, 1. Thus the third position goes 0, 0, 0, 0, 1, 1, 1, 1. And the next 8 positions you're going to see for the first 8, these are going to be 0, and the next 8 are going to be 1s. That's just how the patterns work in binary. I wouldn't get too used to those patterns or too dependent on those patterns, but they do happen that way. Now let's take a look at these numbers. What are they in decimal? Well, you know 4 zeros is probably 0, right? And a 1 in the ones column, or in the 1 column, is 1. Now the second column in binary, as opposed to decimal, is weighted at 2, not 100. So 1 times 2 here is 2. And in the next number, 1 times 2 plus 1 times 1 is what? 1 times 2 is 2, plus 1 times 1 is 1. Well, that's a 3. In this case, 1 times 4 is 4, and the rest are zeros. This is 1 times 4 is 4, plus 1 times 1 is 5. 1 times 4 is 4, plus 1 times 2 is 6. And 4 plus 2 plus 1 is, ooh, that doesn't look too good as a 7. 7. I hope that makes some sense. Let's do it one more time here. This time let's do it with 8 bits. Now let me draw my number line out. Again, in decimal, that number line is what? 1, 10, 100, 1,000, 10,000, right? Messed up here. 10,000. Okay, in decimal, in binary, we might have much smaller numbers to deal with. We deal with 1, 2, 4, 8. Remember, this was 2 to the third. Now, what's 2 to the fourth? It looks like 24 there. What is 2 to the fourth? What is that? It's 16. What is 2 to the fifth? It's 32. 2 to the sixth is 64. 2 to the seventh is 128. And notice they just double each time. 1, 2, 4, 8, 16, 32, 64, 128. Simply a doubling at each interval. Okay, so let's call these our magic numbers. And we can draw this number line the same every time. And because we're only really dealing with 8-bit numbers in the binary we need to understand for network addressing, this will be the number line pretty much every time. Now let's deal with 8-bit numbers. The first number, we'll draw our leading zeros for the sake of simplicity or clarity. The first number in counting is a 0, just like a 4-bit number, same thing. What would the next number be? Well, it'd be 1, of course. So all we're really doing is making the number line up top line up with the number we're desiring here in the right-hand column. The decimal number we're looking for over here in this column simply needs to be added up properly in the binary column in the number line. The next number would be 2, right? Let's go ahead and put our leading zeros out here. Our next number would be 2. And that's going to be a 1 in the 2 column and a 0 here. The next number in sequence would be what in decimal? Well, it would obviously be 3. And what would we use on this number line to get 3? A 1 here, and zeros in the other column. And again, it's simply a matter of incrementing to the available digit. That digit was available when we went from 2 to 3, so we incremented it. So that's what we do when we count. We just increment to the next available digit. And when we look at the number line, we check and make sure we did it right. 1 plus 2 is 3, and that makes sense. The next number is 4. What do we do to get a 4? 1, 0, 0, and leading zeros for the rest, gets you a 4. What would 5 be? Well, 1 in the 4 column, right? A 0 in the 2 column, and a 1 in the 1 column would get you a 5. How about 255? Now, that's the largest number we can represent with 8 bits. There are 256 bit combinations with an 8-bit number, 0 through 255 in decimal. So for an 8-bit binary number, the largest number of decimal combinations available are 256, 0 through 255. Now, how do we determine this? Well, can you put 128 into 255? Yes. What would be left over? Well, let's take a look at that. So if we put a 1 in the 128 position, that would be the same as subtracting 128 from 255, and that would leave 127 remaining. If we put a 1 in 64, can we take 64 from 127? Yes, we can. That would leave 63. Could we take 32 from 63? Yes, and that would leave us 31. Could we put a 1 in the 16 position? Yes. And that would leave us 15. Could we put a 1 in the 8 position? Yes. That would leave us 7. Could we put a 1 in the 4 position? Yes. That would leave us 3. Could we put a 1 in the 2 position? Yep. That leaves us 1. Could we put a 1 in the 1 position? Yeah, that leaves us the last one. So 1, 1, 1, 1, 1, 1, 1, 1 is 255. A number you will see over and over again. So if you want to know, if you're given a decimal number and you want to know its binary equivalent, put a 1 anywhere on the number line that you can. In other words, if you start over on the left-hand side with 128, is the number bigger than 128? Yes. Well, then put a 1 and subtract 128 from the number. Let's do a few others. All right, let's draw the number line again. And let's say I'm giving you a number 146 in decimal. And I want to know the binary number in 8 bits. Can I put a 1 in the 128 position? Sure, because 146 is larger than 128. So I would take 146 and subtract 128. What does that leave me, 18? Leaves me 18. Can I put a 1 in the 64 place? No, because 64 is larger than 18. Can I put a 1 in the 32 position? No, because 32 is larger than 18. Can I put a 1 in the 16 position? Yes, because 16 is smaller than 18. That leaves me 2. So I have a 0 in the 8 position, a 0 in the 1 position, and a 1 in the 2 position because I can subtract 2 from it. And that leaves me 0, so that's a 0 in the 1 position. So the binary number 1, 0, 0, 1, 0, 0, 1, 0 is equal to 146 in decimal. That may not look like it, but that's exactly what it's equal to. Okay, let's do some more counting, just straight counting in binary. Let's draw a number line. Again, we're only going to deal in 8-bit numbers for networking. So let's just start there. Let's not worry about their decimal equivalents for a minute. I just want you to learn to count in binary. So you start with the zeros. What would be the next one? We could increment the 1 position here and provide the leading zeros in front of it. What's next? Well, the first position is full, so we'll set it back to 0 and increment the next available position. So that goes to 1, 0, and we'll provide our leading zeros. What would the next one be? Well, we have room in the first position, so let's increment this one again. You only increment 1 at a time, so let's leave this one alone. And that's the next position. What's the next one? Well, this one's full, so we'll set it back to 0. This one's full, it goes back to 0. And we increment this column. We have leading zeros out here. Well, this one now, the last column is again available for incrementing. So we increment that one. We'll leave the second and third positions alone. Leave the leading zeros out here. This time this one's full, so we'll set it back to 0, increment this one, leave this one alone, and put our leading zeros out here. Now what do we have in decimal? We can look at our number line and tell, but we know what we want, right? I mean, we started at 0 and we're just counting upwards. So we're expecting 0, we're expecting the next one to be 1. Does that make sense on your number line? Well, 1 times 1 is 1, sure. The next one we're expecting to be 2. Does that make sense from your number line? Certainly. The next one's 3. Does that make sense from your number line? 2 plus 1 is equal to 3? Well, sure. The next one is 4. 1 times 4 is 4, plus 0 is 4. 4 plus 1 is 5. And 4 plus 2 is 6. So this makes sense based on we're just simply counting up in binary. Okay, let's continue on. Okay, let me reset my board here. The 6, let's continue counting after 6. We know we're going to have some leading zeros out here. We have position left here now to increment. And because we incremented there, let's leave the other ones alone. 1 times 4 is 4, plus 2 plus 1 is 7. And that makes sense. The next number in sequence would be a 1 here because these 3 positions are now full. So they go back to 0 and we increment the first available, which in this case is 8. So let's again increment the first available position, which in this case is here, and we'll leave the rest ones alone. And 8 plus 1 is 9. Now, this position is full, so it goes back to 0. We increment the first available position, leave the others alone. That gets 10. And something neat in binary, the number 10, 10 there is 10. I don't know why it works out that way, but it does. But at any rate, 1, 0, 1, 0 is 10. So what would 11 be? Well, we have room to increment the first bit. So if we increment 1, let's leave the others alone. And we end up with 11. All right, see if you can come up with 12 through 15 on your own. So go ahead and pause the video and see if you can come up with 12 through 15. Okay, how do you think you did? The 1's position is full. The 2 position is full. The 4 position can be incremented, so let's increment it. We'll leave the 8 alone and the rest of them alone. 8 plus 4 is 12. The 1 position can be incremented. And once we increment 1, let's leave the others alone. 8 plus 4 is 12, plus 1 is 13. The 1's position is full. Let's set it back to 0. Let's increment the 2 position. We'll leave the others alone. 8 plus 4 plus 2 is 14. We can increment the 1 position, because it's empty. And once we increment 1, let's leave the rest alone. That is 15. Okay, see if you can work 16 through 20 on your own. 16 through 20. Continue counting from 16 to 20 and then rejoin the video. All right, let's try 16, see if you got it right. The leading zeros are okay out here. Oops, sorry. Actually, they're not. This position is full. We'll reset it back to 0. This position is full. We'll reset it back to 0. So is this position and this position. The 16 position is free. We'll increment it 1. And 16 times 1 is 16 plus the rest are zeros. So that should be 16, right? So for 17, going up 1, the first position is a 1 because we can increment that. Once we increment 1, let's leave the rest alone. And that'll be 16 times 1 is 16 plus 1 is 17. In the next increment, 1 is full. The first position is full. Let's set it back to 0. Let's increment the first available one, which is the 2 position. Leave the other positions alone. And that gets me 18. For 19, 0, 0, 0 on the leading part. The first position can be incremented to 1. The second position can be left alone since we incremented the first one. Let's write the others as they were. That gives us 16 plus 2 plus 1, which is 19. All right, in the next case, 1 is full, we'll set it back to 0. 1 is full, we'll set it back to 0. We'll increment the 4 position. And 16 plus 4 is 20. So you can just use the number line up top to make it work, or you can learn how the increments work as you're counting in binary. And both ways are good, and you should probably be familiar with both methods because they're necessary. All right, we'll do some more examples in a minute. This has been your first video. We're going to have a second video on binary to decimal and decimal to binary and counting. So keep practicing. Review this video if it didn't make any sense. If you think you got about 80% of this, then go into the second video.